What are we doing?
What do I want to do, or what are we doing?
What do you want to do?
I want to talk about the JZ cams.
Dang, dude! This car's freaking sick, bro! The Fast and the Furious one!
Two JZ cams?
Two
What do you
JZ
want to talk
cams.
about? Like, how deep are we getting into this?
Um, well, we started going over some numbers of what was left on the table with the current restrictions of installed height and bucket diameter.
Yeah.
You said that you could tune that thing up from where it is, from where what the market considers the best camshaft. You said that uh, you could do better.
Okay, well, I don't know if I can do better because I've never done one. So, but I can show you what the numbers look like, and that would it gives me a pretty good idea of where we would land.
Okay.
But I got an idea. There's got to be a faster way to do this. Hang on a sec. Hello.
Oh, hey, Dave.
Cheesy.
What do they look like, Jimmy?
Dorks. They look like a couple of dorks.
Oh man. Okay, we can look at this one. This is the casting cam that you gave me.
Mm-hmm.
So that's the cast cam. That's the steel cam, and then this is the redesign. And so let's just look at a couple things. Let's look at this is real interesting on the casting one. So first of all, on the casting, I could tell that these were designed, like this one was the steel cam was designed for the bucket motor, and then the cast cam I could tell was designed for the tappet motor. And that's by looking at this number. See how they're both the velocities are about the same. It's because they need to keep it on the bucket. So this one has, well, I'll just say it's 209, 209,002, 209,208. And then if we look at the steel, this already tells me that this cam can run, it's designed to run on a bigger bucket. Just that number alone tells me what's going on there.
Okay.
And then let's look. So we have a maximum positive acceleration of 689 on the steel cam. And then on the cast cam, we have 664. That gives us a range of this right here. That's the positive. And then, or that's the opening side. And then on the closing side, this is weird that this is higher than this. Typically, the closing is lower than the opening. Got to calm it down when you're trying to close it. Like you can slam it open.
Sure.
That's all valve spring controlling it, right? But you want to kind of set it down gently.
The similarities between the two. Is there signatures to different men's work?
Yeah, I don't think these are done by the same people. They have a high and a low. That's a pretty big difference there, right? So we have 4 zeros, or is that 2 zeros 1? Yeah, 2 zeros 1, and then 3 zeros 6. So this is like way higher. It's a spike. Okay, this one is more, the steel cam is more reasonable here because
this action in teal is a byproduct of the this waveform as the valve sets down. The other one looks more upset. Yeah,
that's jerk.
But on the cam above, do you see how the amplitude intensity?
Yeah, well, this I took all of these off of measured cams, so that comes off of the Cam Doctor, right? So that's like a 36,000 point encoder that's taken,
okay,
millions
so
readings.
A lot of data.
Yeah,
you filter that out.
This measured would be just
forever.
Totally jagged lines.
Okay,
right. So we could see the acceleration here. These two accelerations are more reasonable. These are more reasonable. They're closer together. In fact, I would say these were designed with equal opening and closing accelerations. This was designed with different opening and closing accelerations, right? And then we can look to see This is the negative acceleration number. 30 is 260. So this negative acceleration is enter this per degree squared. And then,
Okay, I was waiting for that. So that's inches per degree.
right, squared.
So how
This
far
is
is
the acceleration number? And then this one here is minus 0.00275-ish inches per degree squared. A couple things we can notice here, like it's a flat tappet, so we actually care about the nose radius. So we have this 257 nose radius, 266 nose radius there. The steel cam has smaller nose radiuses, 250, 240. So that's gonna be more durable over the nose no matter what, just the size of the radius. Like you can push it, so it literally is like an eighth of an inch radius. It's just like a point.
Yeah, the factory cams look very
Right.
pointy.
So yeah, so what questions or comments do you have just comparing those two things?
Well, so first I'd like to know how big of a difference in numbers matters.
I like them when they're really big.
And I think it's better when they're enormous.
Like you have there's small numbers, so is a tenth matter? Does the thousands, like you have when you go out to 00026? Okay, that's a number that maybe nobody's familiar with. I'm not familiar with. If it was 00028, is that a big change? Is it a big change at 00041? What is the
Yeah, so 28 is less than 10%, right? So I think the easiest thing to do is you start off with the OEM cam, and that when I said limits initially, I'm just sort of like, these are your initial targets. Like if you can duplicate if you could use the same sort of dynamic limits as the OEM cam and then design a cam and then start from there and then see where can you push it before stuff starts floating.
Okay.
Right. So ultimately, between looking at the numbers and then going to the spintron and then trying to like make stuff out of control, we have to empirically find it. Because if you could calculate it, but you know how that works. A lot of times you're calculated and you miss it by the barn door.
Right.
Right. So like I would say in the race engine and performance stuff is you just have to try it, but you have to be guided by the right principles.
You asked for more power, we delivered. Skunk 2 Ultra camshafts for the B58. Built for boost, made to rev. Matched with our Ultra valve springs and titanium retainers, this system is engineered for stability and maximum control at high RPMs. No guesswork, no shortcuts. Just the same race-proven technology we've perfected for decades, now for your B58. Skunk 2 Ultra. Power, precision, proven. Go faster.
Okay. In the flat tappet world, are these? We used some of the Harvey Crane's Word Zero Day with Intensity.
Okay, yeah. So let's take a look here. So we have on the cast cam 2246 major intensity. So between 20 thousandths and 50 thousandths lift, there's a difference of 22 degrees. You could say that if you were to split it in half, it would take 11 degrees to go from 50 thousandths to 20 thousandths. That's another way to say it, right? So on the minor intensity side, you see here we have 44,000. So that would say, okay, from 50 thousandths to, if we had it latched at 10, that's the difference between 50 thousandths and 10. So this 44, you could say, it would take 22 degrees to go from 50 to 10.
I think that
this allows you to calculate your seat timing pretty accurately. All right. And then let's look at this other one. So we have the steel. The steel actually 25.1. So it's actually less aggressive by 3 degrees, or about 1.5 degrees on each side. And that's just like changing the slope at the last. That's like the vert part of the ramp. between 10,000s and 50,000s, let's say that's our whole ramp. That's going from 0 to the point where we launch this thing, right?
If you're staring at the 3 different camshafts, and again, you said that it's measuring so often that there'll be racket or noise on the channel. So the shape of this right here, and this right here, and this right here.
Yeah, so for example, any of these lines shouldn't be riding up and down off of the 0. They should be even up or down. So let me show you like.
So then that's noise.
No, that little bump isn't noise. That's jerk. I can show you a design file, and this is.
Ooh.
So unfiltered, it looks like that.
Wow.
Right. So I'm trying to put as little smoothing as possible, in there just to get an idea of where the peaks are at. I don't care so much about all the exact shapes, but like, for example, if I was to look at this, I don't believe that it dips back down. I don't believe the jerk is doing that, Yeah, but I can only clean it up so much because it's got so much noise in it.
Right.
Right. So if I was to show you a design file.
So in the intensity number, is there a fair share of averaging that goes into gathering that information if there's so much potential for noise?
No, because the 50 lift number is pretty much dead set.
Okay. So
the lift is accurate.
Yeah.
The lift is going to be whatever noise over 36,000 points. You know what I'm saying? So capturing what the number, like knowing what angle 50 is at, what angle 50 is at, 20 is at. If there's any deviations, it's going to be fractions of degrees. You know what I'm saying?
And this cycle is 36,000 points.
Yeah, the encoders, they have 3600.1s and 36,000.1s, and they might even have a higher resolution than
that. So where did you end up? Where were the biggest differences between your design and the existing design?
All right, let me show you what a design file looks like. So this, you can see here, this is the design files are clean.
Sorry.
Oh, you can see here the design files are, you don't see the stuff. So yeah, so if we look at the minor intensity on the steel cam, it's 55.4 degrees. So it's 17 and a half degrees or 17 and 3/4 degrees to go from 50 to the base circle on either side. So what I did as just as a study was I took 444, which is their lift here, 445, and I took their 275 numbers, and I did a 445. Actually, I wanted to hit their same lift and duration, and so I ended up hitting their lift and duration with slightly lower acceleration. And then if you look at the major intensity, 22, and then the minor intensity, 38. So if I'm 37 to 55, I'm 18 degrees different. So if I'm 9 degrees shorter on seat timing on each side, even though these two cams have the same lift and duration, the one with the shorter seat timing is going to make the more dynamic compression. Right. 18 degrees is nothing to sneeze at. Yeah.
Yeah.
So this is essentially what I did was I took, okay, I don't have a stock cam. I have the two cams that you gave me to do. So, okay, if you say this cam is the shit, then let me hit the lift and the duration. So the lift was 444 lift, and the duration was 248 at 39 at 1 millimeter, 248 at 1 millimeter right there, right? So I hit 445 and I hit 248 at 1 millimeter. for all intents and purposes, it's the same triangle,
Right.
but the function's different.
So quantify it into a number, like the cranking compression will change.
I can't quantify it into a number, but I can tell you I have 18 degrees less timing on the seat. So that's automatically 18. Like that's going to be more degrees of compression, so, especially on the intake close side. Right. And then I talked about nose radius, 242, 250 for the steel cams. So I got a nose radius of 280 and 285. So a rounder nose,
Yeah.
less acceleration, shorter seat timing, same lift and duration. If I was to look at it, if I would use 50 numbers on a piece of paper, people would say they're the same cam.
So shorter seat time. Shorter seat time, does that equate to more aggression, or is it hard? Is it how much harder is it to stabilize it with shorter seat time?
No, the shorter seat time. So it's the 50 duration number and the lift number that's gonna be the one that determines kind of like what power range, how it's gonna perform, because that's really kind of the functional range of that camshafts. But that shorter seat timing, the part that you really can't see, that'll show up as better throttle response, more torque, cleaner out the tailpipe, everything. It's just shorter seat time, right? Because once I get past the effective point on the cam, which is let's say 50 thousandths, I want to get it closed as quickly as possible, right? So it's like I talked about, if the major intensity numbers, like the last part of the ramp, that really determines how this lobe is gonna kind of the shape.
Right.
The bottom part, how long do I want the lead in? Right. So like,
But the lead in, the lead in is going to show itself in the jerk.
If I, yeah, you know what? We can do this. Got Squidward. Yeah, you could say that. So if it was this bottom one, so like skating a drainage ditch,
Yeah. You hit a
you fucking like you
change.
hit it.
Yep.
That's the jerk.
You ever take it off any sweet jumps?
Like that's literally if the trend. So this is like the transition is basically how is it loading up as it's going up the ramp.
Okay.
Right. And the jerk would this kind of determines the shape of how it leads in. Determines
Ready
the
whenever
jerk.
you guys are.
Okay. Yeah. So it's kind of funny because I'll have like on other cams, not these cams, but different cams, I'll have the same. Let's say they have a good minor intensity, but I'll actually have the same minor intensity but a higher major intensity, because this part might be the same, but I might crank it up.
Right. So you said it was 18 degrees of crank rotation.
Yeah. So this is 37 degrees minor intensity. This one's 55 degrees minor intensity. It's off by 18.
And when you do that, you're effectively changing the overlap because you're putting the
We're changing the seat timing. So like the 50 number is good for setup, but the engine actually functioning off of when the valve actually opens and closes, right? Because if you don't close the valve, it's leaking air. So it's sort of like you got this cam and you close it, and then at the very end you have this long tail on it that closes real slow. Like if it's on the compression stroke, you're just pushing it out.
Right, but when we talked the other day, the closing has to be respected because you're in this situation of a decreasing valve spring pressure, right? So you're setting it down.
Right.
So if you set it down faster, doesn't the valve want to bounce more?
Yeah, that's the seating velocity. So like when you design the ramp, you have different seating velocity heights. So for example, okay, so this is a velocity curve here, right? And you can see this velocity curve goes here, and then it goes constant, and then it goes down. So this section here, this constant. So that's like, this is a seating target. We want, no matter where the lash is on the engine, we want it to be able to seat at this range. And that's why they make the long constant velocity ramp. Because they're not, so it's like, they're not sure what the lash is at. So maybe if they make this super long handicap wheelchair ramp, you would never have an impact.
You're in trouble.
You know what I'm saying? And I'm actually, I tried to set like, I try to make it so I can set it all the way up from this point, all the way down to this point. And if you look at it, see, I don't have no constant velocity here on this side. No, I don't have a constant velocity on the opening side. And then I have a constant velocity here on the closing side. It's really short. This constant velocity is only this long. It's even shorter than that.
Man, it's interesting to sit through these things with you because there's so much information that I've never been explained.
Nobody explains this.
Right. So there's some processing time involved, and you're talking about, okay, constant velocity. That's this. Is that effectively time for it settling down?
So I have the seating velocity that's in inches per degree. And then there's actual impact velocity, because you'd have to take your inches per degree, and then you'd have to multiply it by the actual RPM at that, you know what I'm saying? The speed at that RPM.
Mm-hmm.
So there's the seating velocity, which is not RPM dependent number. So none of these numbers here are RPM affected. They're just numbers, right? And then the impact velocity is after, like, the impact velocity changes according to the RPM. The seating velocity doesn't. The cleaner your engines are, the better they seal, the more power they make, they all start to sound like a chainsaw.
A lot of the stuff that we've discussed is the first time I'm ever getting it. So on one hand, I'm trying to take it in and let it make sense to my mind and be able to put it to use. And on the other hand, at the same time, I'm thinking like, holy shit, how cool is this?